So I'm very excited to introduce our speaker tonight, Dr. Arpita Roy. She got her bachelor's degree from Franklin and Marshall College and her PhD from Penn State. And she's now a Millikan postdoctoral fellow here at Caltech, where she works on building next-generation instruments for exoplanet detection with the goal of being able to find small planets just like the Earth. And a fun fact about her is she is currently involved with no fewer than 6 new instruments around the world that are going to be pointed at the sky within the next few years. So, thank you all so much for your attention, and please join me in welcoming Dr. Arpita Roy.
Thanks, Denise, and thank you all for showing up. There's a lot of people here. It's a little intimidating, but are we going to dim the lights a little? Oh, yes. So I have 30 minutes tonight to try and live up to my somewhat ambitious title here, but I'm going to need your help, because this lecture is going to be less about me talking to you and more about me giving you sort of the landscape of the research I work on so that we can all contemplate together what it is that we are finding out in the universe and what that means for us now and going forward as a race. So we're going to talk a lot about witnessing the exoplanet revolution. Those are some big words, so let's break that down a little bit. So let's pause for a little on this word revolution. It's a powerful word, conjures up a lot of images, maybe of bloody battles or political overthrows, or even scientific revolutions where we sort of change the way that we think about certain scientific concepts. But what I want to offer to you today is that what we are witnessing now is not just a scientific revolution, but really a revolution of how we define and understand ourselves in the context of the universe. And it's, there's images of blood, sweat, and tears that come up when you think of past revolutions, and this has its share of tears, especially grad student tears, but hopefully not a lot of blood, even though people in the past have lost their heads for arguing for some scientific ideals, but what we are witnessing now is maybe a fundamental shift in how we understand ourselves, and that's sort of what we're going to focus on today, even as we look at the science. And of course, ask me questions about the science, but I also want you to think really deeply about what this means for us in this moment in history. So this is a picture that is pretty iconic called the pale blue dot image, which shows where we see ourselves right now. Looking back on ourselves, what do we see? So this is an image taken by the Voyager spacecraft as it was leaving the solar system, and it's part actually of a series of pictures called the family portrait of the solar system. But Carl Sagan actually is the one who insisted that Voyager take this image, and so Voyager looked back and tried to find the Earth. And do you see the Earth in this image? Yeah. It's pretty tiny. It's right there. It takes up literally 1 pixel on this image. These bands of light you see are actually aberrations from the camera optics, so it's sunlight bouncing around in there. But that tiny dot, that's the Earth seen from the edge of the solar system. So not that far away. That's our solar system. And it's a tiny dot. It's a little bit blue, and that is the color of our Earth. It's covered by oceans. It has a rich atmosphere. There's a lot of vegetation, and overall, seen from really far away, we are a tiny pale blue dot. And Carl Sagan said some very profound things about this image, including the fact that this is our home. So you and I and everybody we have ever known, all of our forefathers and foremothers, every war, every great piece of art, everything that we cling to as our history, as our civilization, happened on that tiny dot. So there's a lot more going on in the universe. We are a very, very small part of it. And that, I think, is a really humbling thought. We get pretty caught up in a lot of everyday things. And so something I appreciate about my science is that it makes me remember this image and maybe take some of these fights among ourselves a little less seriously, but also zoom out and think about why we're here, and also maybe a little bit of who else is here. And so humankind has for ages looked up to the stars and asked a lot of very fundamental questions, one of which is, are we alone? Almost thinking, as I look up to the stars, is there someone out there looking back at me? And this is a question that for many, many centuries lived in the realm of philosophy, of fiction, of imagination. It wasn't something science could really touch, because this was a profound and difficult question, and we just didn't have the tools to answer it. And so what we did was we did use our imaginations, right? There are histories of people in the 1400s and the 1500s. Famously, there was a philosopher called Giordano Bruno, who in the 1500s proposed that maybe the stars out there were suns themselves and had maybe worlds going around them with life on them. This was a heretical thought at the time, and he was burnt at the stake for thinking it. But that didn't, stop us imagining these other worlds and other beings. And so from Giordano Bruno to things like Star Trek, we've always been imagining what other planets could be like, what aliens could be like. We've all seen depictions of aliens in lots of movies. But I will stress that so far as the scientists know, we are alone. Ancient aliens might tell you differently, but scientifically, we don't have any hard evidence that there is life out there. There's a lot of hope and a lot of maybe statistical hope. But exoplanets, the study of exoplanets in the larger scheme of astronomy, more than things like studies of galaxies or black holes, are very evocative and touch something inside us, because exoplanets are things we have been imagining and are easy to imagine because they are places. They remind us of our home, and they make us wonder if there are other beings who have other homes like our own. And so thinking of them as maybe destinations that we could one day go to makes them a much more powerful thing to find in the universe than these other much more abstract, complicated things. This is a familiar feeling, finding a planet, a rocky planet that's just like our planet. And so even though we were thinking about exoplanets for centuries, forever it was really hard to actually imagine finding them. We had sort of retired ourselves to the fact that they were always going to be a figment of our imagination. There were a few claims of exoplanets found around the 1950s, but they were found to be wrong. And then people really backed off on claiming any exoplanets. And the reason even scientists thought that we might never actually detect exoplanets is because they're really, really hard to see. Even theoretically, you can figure out that it's very hard to find them. Why is that? It's because they're tiny balls of rock, especially the ones like the Earth. So they have no light of their own, and they're next to these stars, which are huge burning balls of gas, and they're really, really far away. And so you can imagine light years away, a giant ball of fire with a tiny rock around it. You don't really see the rock. An analogy we like to use is it's like trying to find a firefly next to a lighthouse. You don't see the firefly, right? And maybe you will never see the firefly. But 2 decades ago, right around 1992, 1995, astronomers were making lots of technological advances, and some of them started to work. And For the first time, technology aligned with some of these big questions that we had been asking for centuries, some of these fundamental questions of humanity, and gave birth to what we call modern exoplanet science, which is what I work on now. So the first successful detection method for exoplanets is what we colloquially call the Wobble method. So the idea here is that as the exoplanet goes around the star, it gravitationally tugs on the star tugs on the exoplanet, and there's mutual gravity. The exoplanet makes a big circle because it's small and it can respond to that gravitational force by moving a lot. The star moves just a little bit in response to the exoplanet, but it does move. And so all stars that have exoplanets are wobbling just a little bit. And so if you can detect the wobble of that of the star, then you can infer the presence of the exoplanet even though you can't see it. So other names for this technique are the radial velocity method, where you see the velocity of the star along your line of sight, or the Doppler method. If you remember hearing about the Doppler effect in physics class, this is the Doppler effect of light. And so the light gets a little bit red and a little bit blue as the star wobbles around. So ever since 1995, when we found the first planet using this technique, there's been a lot of advances in the last 20 years. This is an exponentially growing field. And so since then, we've actually gotten quite good at looking for exoplanets, if I say so myself. And so let me show you what that looks like. So here's a history of exoplanet detection. And this graph is moving over time. So you can see in the 1800s, there's solar system planets. We're at 8. Finally, we're at 9 with Pluto in the 1920s. And then just around the end of the 1990s, we start finding planets outside the solar system. And then this Kepler instrument is launched, and it just blows up. And so we're at about 4,000 or 5,000 planets right now. That's a lot of exoplanets, which means you can start asking some questions about generally what do exoplanets do. So we've detected a lot of exoplanets, but we've also detected a lot of different types of exoplanets. So this is an image, an animation showing all of the planets found by Kepler in the first few years that it was in the sky. And there you have the solar system for scale. And these are all multi-planet systems, so systems with more than one planet, and the planets are actually to scale. So you can see there's some kind of big ones, bigger than we have in the solar system, some really close ones that make these weird wobbly patterns. Basically what you're seeing here is there's many different types of extrasolar systems than we imagined when we were just looking at our own solar system. So we have this very rich data set to look at now, and ask questions about planets. So that's what's happening right now in astronomy. We are basically redefining our understanding of many things that used to be just based on the solar system, but now we have hundreds of planetary systems, thousands of planetary systems to look at. So we can ask better questions and have better answers of things like how do planets form, what kinds of planets are there? Turns out our solar system doesn't have every kind of planet. We're finding planets that don't exist in the solar system. There's also weird things like rogue planets, so planets that have been shot out of their solar system and are just kind of floating around by themselves. That's an interesting question for hosting life. Probably those are dead planets, but maybe there's some really clever race on it that figured out how to mine energy from the planet. Also moons, we're not quite at the place where we can detect moons yet, but we certainly know from the solar system there are some very interesting moons that could host life. So what's next? We stand here with, say, 5,000 planets in our back pocket. Where do we go from here? So importantly, still alone, right? Haven't found life. This big question still remains. Are we alone? Where can we find other life in the universe? And as an aside, what is life exactly? Turns out that's a pretty difficult question. Till now, we didn't super have to answer it because life Most of the time, life on Earth is pretty obvious or definable by a few parameters. You know, it moves, it grows, it dies. But when you can't actually watch that life over its lifetime or look at it with a microscope, how do you identify life? How do you define life? And so we start by looking for something super obvious, something that is integral to life on the Earth. Can anybody guess what it is? Just shout it out. Shout it out. Movement. Energy, cells. Okay, so some of these things, some of these things would be great to find, like if we saw movement or cells, but we can't, remember, the star is really far away, so we can't actually see the planet. So water, I heard a lot of water. Water is where we start, because most kinds of life on Earth require water. And maybe some of you will say, hey, I know some kinds of life that don't need water. And those are cool too, because we can look for those when there's no water. But mostly universally, it's not an accident that life on Earth requires water. Turns out water is present across the universe in places you would find surprising. And life is actually very resilient. Life will arise wherever it can on Earth, even in like nuclear sites and acid lakes. And so there's a good chance there's life out there in the universe. The question is, how do we find it? And so we start by looking in what we call the habitable zone. So this is basically the distance from the star, where the heat from the star gives the planet a nice temperature, think like Florida. And so it's literally not too hot and not too cold for life. So this is also called the Goldilocks zone, because it's comfortable. And so that would mean there's liquid water on the surface of the planet, and so maybe there's life on the surface of the planet. So it's important that the life is on the surface of the planet or does something to the surface of the planet, because we can't see deep inside the planet, right? The other thing we think we want is a rocky planet. Earth is certainly rocky, and so we think it's good to have a rocky planet. It's possible the gas giants have some kind of life, but it's not life we're familiar with. So we're starting with the rocky planets. But turns out the Earth, or rocky planets like it, are pretty small. So even though they make their stars wobble, it's a very tiny bit. And it's actually crazy how tiny it is. So it's about 10 centimeters per second. So 10 centimeters is about that much. So every second, it moves 10 centimeters. That's slower than you walk. It's actually about as slow as a tortoise. So think about how slowly a tortoise walks. That's how much the star is moving, and it's light years away, right? So we're trying to detect this tiny motion in the star over time, but it's only moving a very little bit. So that means we need to be really clever about it and come up with a lot of great new technology. And we are doing that. So this is a figure I made from a conference we had about 5 years ago. And what I'm showing here, the resolution isn't great, but these are 23 new instruments that were presented at that conference that were going to go on sky in the future to look for small exoplanets. And what I'm also showing here are the ones that are figures, are some space missions that are going up along this timeline, and the ground-based missions and the space missions sort of work together to give us all the information that we need to figure out if planets are habitable. And actually, we had another version of this conference just this year, and the most amazing thing is all 23 are still going, because usually funding means a lot of them die along the way, but we're still going. All 23 are going, and pretty much they're on schedule. So we are about here with the 2019 instruments coming online. And just to give you a little idea of what I work on, these are the 6 instruments of those 23 that I work on. Some actually pay me to work on them, some I do for free, but these are very exciting because they're all next generation instruments that are going to give us new insights into the kinds of planets we're finding. And so just some pretty pictures of the observatories where I'm building these instruments, and these are all around the world. And also to show you that each instrument has something special about it, because it's hard to justify building a new one unless there's something special. There's this one in Texas that actually is on sky now, which is getting unprecedented precision on red stars. So this is a near-infrared instrument. So it can look at stars that are much redder than the sun. Turns out there's a lot more of them, so that's good because you have a bigger sample to look at. One that I'm working on here is called the Keck Planet Finder, which is going on the Keck telescope in Hawaii. This is a big 10-meter telescope. And interestingly, we're building an all-glass spectrometer for it. So every bit of the spectrometer is actually made from glass, down to these little balls that we use to align things. So that's pretty amazing. Here's one in India. That's cool because it's on the other side of the world. So when it's daytime here, that telescope can take over. Just a lot of exciting things happening. This is another great one called NUIT that is coming online in a few months. My favorite quote about it is that it's the most stable ton of matter ever made by humans. So there's a lot of exciting stuff happening in exoplanets. What does that mean for the future? So to correspond with our last animation of the past history of exoplanets, here's the future of exoplanets. It's going to go pretty quick, so watch it. This is an optimistic estimate, but if all of the instruments and missions coming online live up to their promise, in some years we'll be at 100,000 exoplanets. And so you can really ask your difficult questions at that point because you have 100,000 points of data to try and answer some of these things. And so I will bring us back to this idea that we are witnessing a revolution that is in motion right now. We've already sort of changed the way we understand our place in the universe, but the journey isn't over. We're actually very rapidly going forward, finding new things, and we're probably in our lifetimes going to answer questions that we almost dare not ask yet. But the more evidence we have, the more confidence we will have to ask some of these questions that seem sort of still sci-fi-ish right now, but might very realistically be answerable in the next few decades. And so extraordinary claims, of course, require extraordinary evidence. I was Googling this. Turns out this is an acronym, ECRI, that people use. I didn't know it was that popular of a phrase, but and so when we do claim that we have found life on another planet, first of all, it's probably not going to be little green men walking around, right? It's going to be bugs or bacteria, something that's not apparently very exciting, but is still actually paradigm shifting in the fact that we are not alone in the universe. Of course, if we did find intelligent life, that opens up a whole other can of worms. But all of these are exciting and really evocative things to think about. And so I have a question for you, because this is not just me talking to you. This is all of us thinking about this together. Is what would actually convince you that we have found life on another planet? So some of these questions should be answered by scientists who look at the signatures of life on Earth. But life is actually something we understand instinctively and something we recognize instinctively. And so it is absolutely fair for all of us to weigh in on this question. And also as a side question, what would that mean to you? So I'd love to hear from you. I think we have a mic to pass around. When the scientists published their first finding of life, what would make you say, yeah, that sounds real? Yeah.
Well, I would be looking for characteristics of life on Earth, like basic characteristics, such as movement in one form or another, the requirements of energy, the requirement of water in one form or another. Well, there's some exceptions, but ignore those exceptions for this point.
Yeah.
Like the requirements of energy, some basic cells at least, and yeah. And to me, it would mean that we are truly not alone in the universe, and there is possibility for insanely advanced technologies because of like I don't know how you would put it, interplanetary exchange.
Yeah.
I don't know.
That's a lot of things to ask for, but that's good. Anyone else? Is finding water enough? Is finding oxygen enough? No, because oxygen actually can be produced by abiotic means. What else? Radio waves. Some astronomical objects give off radio waves. A particular kind of radio wave. Yeah, maybe a pattern of radio waves that doesn't seem natural. There have been claims of things like the wow signal in the past. Yeah.
I've often heard it said that we've been transmitting radio and television signals for 60, 75 years, depending on, so that 60 light years away, an alien civilization might intercept I Love Lucy.
Oh, I was going to use I Love Lucy as an example. That's kind of crazy.
So what would convince me would be Alien I Love Lucy.
Yeah. What would that look like, though?
It would look exactly like our I Love Lucy.
Alien Lucy, yeah.
Except in color.
Because they're a little bit more advanced. Yeah. Yeah, what else? Yeah, so that is true. There is an expanding sphere of our radio emissions that are moving out. What else? What else is a signature of life on Earth? If you were to look at the Earth, how would you know it's inhabited? Yeah, hang on.
Some form of agriculture, like plants or some form of being that would harvest
vegetation.
Yeah.
Vegetation is a super important marker of life on Earth. So actually, if you were an alien looking at not a too far away alien, but a kind of close by alien looking at the Earth, and you were able to take a spectrum of the Earth, just the light coming off the Earth, one thing you would see is what we call the red edge of chlorophyll. So at a particular wavelength, there's this big drop that happens because chlorophyll starts absorbing all of the sun's energy. And for Earth, that's a really important, what we call a biosignature. So if we saw exactly that, that would be great, because that would mean there's literally like plants with chlorophyll on another planet. It's unlikely, but it would be cool. Yeah, did you have an answer?
I'm just trying to redefine what life, what complex life.
Do you want to speak into the mic so we can get it for the recording?
Yeah, I was just trying to define what level of life, very simple life forms or complex life forms. So when you ask that question, are we talking about
all
lichen growing on rocks, or a super advanced civilization that can travel interstellar distances? That's a huge word, life.
Yeah, so the answer is really any of those, right? Because we're looking for all of those in different ways. And they would require different kinds of evidence. So for example, for I think intelligent life, we would need a signature like maybe a laser that's coming at a certain pattern and that we know can't be produced by natural objects. That would mean intelligent life, which is
or
cool.
Extraterrestrial probes that civilization sent out, like we have.
Right. Yeah.
We probably have a better chance of being detected by what we have thrown out into the cosmos.
Yeah. Definitely a place to begin is imagining they're just like us and looking for those same. What would we send? Look for that. Yeah. All right. Maybe one last answer.
This may be a bit unconventional, but I want to see fossils because it's the very not timestamp, but signature element of life that it actually changes and evolves.
Right.
And that's the point of fossils. And when you think about it, life adapts to its environment. It reacts to it. It's like all life. I mean, even like bugs, mammals, all alike. They react to their environments, and over time, their children, are evolved to it, such as natural selection. So that would be a very, very strong indicator to me.
Yeah, so that's hard for exoplanets, at least with current technology, but it's certainly something we can ask of solar system planets, whether we can maybe go to those planets and send things that can dig into maybe the ice or the earth and look for things like that. Yeah, that would be very cool. All right, so I'm going to turn it back to you now if you have maybe a few questions to ask me before we go to the panel. Yeah.
So you mentioned rogue planets. That some exoplanets are rogue.
Mm-hmm.
You mentioned some exoplanets are rogue planets, so they're not actually orbiting any particular star or star system. How do you detect rogue planets? Because, as I understand it, the methods that we use for detecting exoplanets generally involve, some version of triangulation with the star that it's orbiting or some other object. And so, whether you're looking for a transit or radial velocity or microlensing or whatever, if the rogue planet is really far away from any star, how can you be sure of what you're seeing, and how can you be sure that it is not, in fact, orbiting something?
Yeah, so that's a really good question, because almost all of the planets, so all of the methods of looking for exoplanets basically looks to the star. But there is one method, which you actually mentioned, which is microlensing, that relies not on the light from the star, but the gravity of the object. And so that's how we found rogue exoplanets, is because they have less gravity than the star, but they do still bend light around them. And so if you're looking at a star and a rogue exoplanet moves by, you actually see the star brighten just a little bit because of that exoplanet.
Well, so my question was, how do you know that it is a rogue planet as opposed to a star that's orbiting, a planet that's orbiting that star at a great distance and it's bending the light from the star?
Yeah, so that's a very difficult question to answer, and you usually don't know that answer for a while. So you can rule out, areas of parameter space as you observe the star, because the planet hasn't come around, so that planet isn't X distance from the star. But most of these are usually single events, and so many of them look like rogue exoplanets, but it's really hard to find those exoplanets again with any other method. And so it looks like there are some rogue exoplanets we found, but it's hard to be super conclusive about it. Mm-hmm. Yeah. Oh, sorry. Go ahead, Denny.
Well, okay. Let's take maybe one or two more questions, and then we'll save the rest of the questions for our panel. All right.
I think.
Who was first?
I think the guy in the white T-shirt.
So I know that distance is the greatest barrier we have to reaching these places, as you mentioned. I guess I'm wondering what the potential is for terraforming at this point, and shouldn't we be doing it, as soon as possible?
Terraforming planets like Mars, you mean, close by planets?
And even further.
Well, so the ones we can't get to, I don't have a good answer for, because those are huge barriers. We would have to travel so many more magnitudes faster that we don't really have a good plan for that yet. But the question of terraforming maybe planets in the solar system is one we can sort of begin to ask. And there's certainly movies about it, right? Going on Mars and growing corn or whatever it was. And why don't we do it? That is a funding question that is way above my pay grade.
When you asked your first question, how might we detect life?
Yeah.
We were kind of joking. We say, well, you'd look for garbage if it was civilization level. But that actually made me think of a serious one.
Yeah.
If a civilization produced a type of, let's say, air pollution, do we know that there are types of pollution that would have to have been artificially created and couldn't happen naturally that we could detect, say, spectroscopically?
Yeah, that is a very insightful question because you got to something that actually is a pretty recent idea that is being worked on actually by one of my advisors in grad school, which is that every civilization, no matter what stage it is at, produces waste heat. So it takes the much hotter, bluer light from its star, processes it, and then re-emits it at a longer wavelength at a lower energy. So even we take in all sorts of things to create energy. We eat, and we give off infrared radiation, right? That's much redder than our eyes can see. But if you had an infrared camera, you'd see, animals and humans moving around. And so this is a signature of a planet that's inhabited. So the Earth gives off infrared radiation that is much redder, much lower energy than what it receives from its star. And so if you saw a star or the light coming out of it suddenly much more redder than it should be, then it would make you wonder if there is something artificial using up part of that energy and re-emitting it at a much lower energy wavelength.
All right. Okay. Thank you all so much for your insightful questions. There will be opportunities for many more questions in just a moment. But for now, please join me in thanking Dr. Roy once again.